Wagwan people, and welcome back to Kevin Does Physics. In today's episode we are going to start the series by looking at thermal physics. This is chapter 5.1 in my textbook and chapter's probably something in yours. And as I did say in the other video, this is all for the OCR Physics A spec, but it's probably relevant to what other spec you are doing. So let's start off by looking at the formulas you'll get given in the formula booklet for this chapter. If we look at module 5 thermal physics, you get given E equals mc delta theta and E equals ml. But there aren't really much maths to this chapter, but that's what you get given, and we'll look at those in more detail when we get to the relevant chapters. So let's start off with a basic explanation of what temperature is. Temperature is obviously a measure of how hot or cold something is, that's quite obvious. But what you may not know, or well, which you should know, is that an object with a high temperature may actually have a lower amount of thermal energy than an object with a lower temperature, and that will all be explained later. Also important to note is that in physics, degrees Celsius and degrees Fahrenheit aren't really useful. Degrees Fahrenheit can just fuck off, we don't care about that really at all. We have a new temperature unit called the Kelvin, and to convert between Celsius and Kelvin you just do Celsius plus 273 gives you the same value in Kelvin, and that is useful because 0 Kelvin is where an object has no thermal energy at all. This state is known as this temperature is known as absolute zero. It's also not important to note that 1 Kelvin, well, the change of 1 Kelvin is equivalent to a change of 1 Celsius. Okay? Thermal equilibrium. As you may know, like if you open an oven door, basically, temperature likes to be the same everywhere. If you have a hot area and a cold area, and you let them into each other, the temperature will all try and change to reach a thermal equilibrium where everything is the same temperature. Yeah, I hope that makes sense. Moving on, solids, liquids and gases. Matter can exist in 3 main phases: solid, liquids and gases. If you're into physics you may know of things like super solids, super gases or whatever, but it's not really anything to worry about at this stage, and if you go on to do physics at degree level or whatever, somebody else can teach it to you there. A simple kinetic model, as it's known, of matter can basically explain these different phases. In solids, the particles, the molecules or the atoms are held together by strong interatomic forces. Good word there. Solids have a definitive shape. I mean, you have malleable solids and non-malleable solids, but you can't pour a solid, and traditionally they have a high density. Particles in a liquid are free to move past each other, so whilst in a solid, particles will often be held maybe in a lattice structure, in a liquid particles can flow past each other. This basically allows the liquid as a whole to flow, and these will have traditionally a lower density to solids. Of course you have high density liquids like mercury and lower density liquids like water. In gases, the particles are even more spread out, and the particles move randomly in all directions. Basically, if you had let's say a huge box of particles, you would expect them all to sort of cancel out. Yeah, that's probably not the best explanation, but just think about that. And yeah, gases obviously can flow, and it's brilliant. And here's a picture which can explain that to you people who like pictures, because pictures are good. Yeah, molecular spacing. So a density of a material is the mass of one molecule times by the number of molecules in 1 cubic meter. That's just the formula. I don't think I've seen that formula really being asked for a lot, but it's a formula. The mass of a single molecule will never change, because I mean, like, but let's take an oxygen atom. An oxygen atom weighs the same as any other well, let's say an isotope oxygen 14, I hope that's a thing, will always, no, nitrogen 14. A nitrogen 14 atom will weigh the same as every other nitrogen 14 atom. I hope we can all agree on that. So, yeah. So that makes the number of molecules directly proportional to the density. And we're going to cut there, see you in a minute. Next we're going to look at when objects change phase. When objects change from a liquid to a solid to a gas, and whatever. So to change the phase of an object requires the input or output of energy. Input to make something go from a solid, liquid, or liquid to gas, and obviously output of energy, well, taking energy away from it for the other way around. As I wrote there, evaporation and melting are caused by an increase in thermal energy. And this is due to when you input thermal energy, this can increase the molecular spacing of the molecules, which will allow the particles of the molecules to overcome the interatomic forces between them, and then that can allow particles to flow past each other and will no longer be held in the strong lattice structure of a solid, for example. So here's another picture, and this basically shows that as energy is inputted, temperature would traditionally increase. But during phase change between melting or vaporization, the temperature doesn't actually increase, even though you were trying to input thermal energy. This is due to the thermal energy being used to change the phase, not actually increase the temperature of the object. This is explained in a bit more depth further on. Internal energy. Internal energy is defined as the sum of the randomly distributed kinetic and potential energies of all the atoms or molecules in a system. And as you may have guessed by the way I said that, I haven't learned that, but that is a definition that you may be asked in an exam, and you really want to learn that definition word for word. And that definition is taken from my textbook, so 100% correct. Unless I've copied it wrong. But yeah, that should be correct. The kinetic energy from the movement of particles in a system. So in a gas, the kinetic energy is the particles moving around the room. And then in a solid, particles still have kinetic energy, but it's just a very fast vibration of the particles in their lattice structure. The potential energy is stored in the intermolecular or interatomic bonds between the particles, and then this potential energy can be released during phase change when these bonds are broken. And it's also important to look at the internal energy of a gas, because it's very specific, and what we sort of have here are some normal distribution curves. So when an object heats up, the kinetic energy, or the molecular speed in this case, increases overall. And if you were to have a look at the potential energy of a gas, that is very small. 0 in an ideal gas. And yeah, I'm sort of losing myself here, but the graph I said there was the Maxwell-Boltzmann distribution, and we'll hear a bit more about those two guys throughout this series. But yeah, basically the number of particles with each molecular speed increases as you go along, and basically the hotter a gas is, the more kinetic energy it is, and it's kind of normally distributed. But there will still be some objects with a low molecular speed. It's quite hard to explain, and I probably should revise that. Internal energy and phase change. As I have said probably twice already, during phase change, the kinetic energy of a body doesn't change, because the thermal energy is used to actually break the intermolecular forces. This means that whilst total energy increases due to the potential energy increase, the kinetic energy doesn't increase. Wow! Okay, moving on to Brownian motion. Brownian motion was discovered by Robert Brown in 1927, and he decided to name it after himself, as so many physicists do. He used a microscope to examine particles in pollen grains, and he noticed that the water and pollen particles moved past each other. And Einstein, that clever dude, later explained that this was due to collisions from pollen to water particles, and this was sort of like the first definition of Brownian motion. So kinetic model of matter tells us that in all objects the particles will be moving unless we're at absolute zero, which is, I think, in the physical world impossible. Just like in theory we could, but I don't think anyone has got there. Even in like space, you're still going to be getting maybe 2 or 3 Kelvin, I think. In a solid, the Brownian motion is in the form of the random vibrations of the molecules, but the molecules themselves do not move because they are stuck. Break time. Whilst in a liquid and a gas, this is mainly in the form of the transitional movement of the molecules actually moving around in random directions. And as I said before, in a gas or a liquid, all the particles should be moving completely randomly. They'll be hitting walls, they'll be bouncing off, and if you left them if there's like a breeze or some wind, of course that's going to push them. But if, let's say, they were all in a closed not a vacuum. If they were if there was some gas in a closed box, they should all be moving in random directions. And yeah, let's just click on there. Specific heat capacity, and this is where the formulas I talked about around 10 minutes ago come into case. So you have E equals mc delta theta. E is the change in energy. This is the thermal energy you put into an object. Mass is the mass of the body you are trying to heat. C is the specific heat capacity measured in joules per kilogram per Kelvin, and that is a property of a material. As you can see in the table in the bottom right, every different material, aluminium, copper, iron, etc., they all have their own specific heat capacity. And delta theta is the change in temperature in kelvins, or obviously in Celsius, because for this case nobody really cares. So specific latent heat. And just going back to the previous slide, specific heat capacity is basically just that. You just get some numbers, you plug them into the formula, and you'll get three things. You maybe have to look at a graph or something, but you'll get three parts, and then you can work out the last. Specific latent heat. This is what specific latent heat is, sort of like the heat which isn't really there, but is there in hidden form, because this is the thermal energy you've put into an object to make it change phase, but this energy hasn't actually gone into increasing the temperature. Yeah, so the latent heat of an object will be, well, the latent heat of fusion is the thermal energy you need to put into an object to make it go from solid to liquid, and the latent heat of vaporization, I think I spelt that wrong, is the energy required for an object to go from liquid to gas. Of course, you could do it the other way around as well. Let's continue specific latent heat, and this is the last part of this video. As I said before, objects do not change temperature during change of phase, as this wonderful graph says, but however, due to the internal energy does increase, this will increase the potential energy, and the overall energy has been increased. For specific latent heat, E equals ml, where the energy divided by the mass. So let's say you had 1 kilogram of mass. The latent heat is the amount of energy required to put into that 1 kilogram of mass to make it change state. In this case, either from a solid to a liquid, or a liquid to a gas. Thank you for watching this video. I hope it's been somewhat informative. It's been informative to me, which, as I said in the introduction to Kevin Does Physics, is the overall reason for this. So I hope you have enjoyed, and I'll be back soon for some more physics content. Bye bye.